In section 2.4, we look at the chain rule. And so in addition to the product rule and the quotient rule, there are certain functions where we have to use another rule, and that rule is called the chain rule. So if you have a function, let's call it p of x, and that function is built on a function living within another function. So you have f of g of x. This f is the outer function, and the g is the inner function. So an example of something like this, you can see right there in example number 1. You have x squared plus 4x plus 5 raised to the 7th. Raising something to the 7th is an outer function because it's what you do after you do the inside being x squared plus 4x plus 5. So how do we find the derivative of this? Well, the derivative, p prime of x, is equal to f prime evaluated at g of x times g prime of x. So it's f prime of g of x times g prime of x. So it's the derivative of the outer function evaluated at the inside function, then times the derivative of the inside function. Let's do some examples. So I'm going to do example number 1, sort of the long way, and then I'll walk you through how we sort of think about it in the short way. Example 1 says, let p of x be equal to x squared plus 4x plus 5 raised to the 7th. If you had to think about what the outer function is, and we'll call that outer function f of x, what would that be? Well, as a function, you are taking something and raising it to the 7th power. So that would be x to the 7th. The inner function is what you are raising to the 7th power, and that would be x squared plus 4x plus 5. And then we need the derivatives of these. So the derivative of x squared is 7x to the 6th, and the derivative of the inner function is 2x plus 4. Now we put this together, and p prime of x is equal to the derivative of the outer function, which is 7x to the 6th. But we're not going to write the x. We're not evaluating the derivative of the outer function at x. We're evaluating it at the original inside function, the g. So what goes here is 7 times something to the 6th, and that something is the original inside, x squared plus 4x plus 5. So we have 7x squared plus 4x plus 5 raised to the 6th times the derivative of the inside function, which is 2x plus 4. Don't forget to put that in parentheses because it's an expression with more than one term. That is the derivative, and then you would clean it up a little bit by simplifying the 7 and the 2x plus 4. Notice that you can't send the 7 inside the x squared plus 4x plus 5 to the 6th because that is raised to a power, and exponents take precedence over multiplication. You can, however, multiply the 7 and the 2x plus 4. So if I multiply that out, I get 14x plus 28 times x squared plus 4x plus 5 to the 6th. And that's the derivative. And that is the chain rule. Now, I told you I would show you sort of how we think about it when we just sort of do it without writing all of these steps out. We don't really do that. We just sort of think about it in our heads. Let me show you how to do that. So in this case, it's a power rule. And the power rule says, bring the 7 down. The inside stays the same. Lower the power by 1 times, and then multiply by the derivative of the inside, which is 2x plus 4. So that's sort of how I think about it in a stream without regard to having to super analyze which one is this, which one is that, how do I take this derivative, and things like that. I see a power rule because the power is the last thing that happens. And so the 7 comes down, the inside stays the same, lower the power by 1, and then take the derivative of the inside. Let's see some more examples. Example number 2. Let p of x equal the square root of 6x minus 7. Find p prime of x. This outer function is the square root function. And you may recall that the derivative of the square root of x is 1 over 2 square roots of x. That was one I asked you to memorize earlier. So we're going to use that now, except the inside is not x, it's 6x minus 7. So p prime of x is equal to the derivative of the outer function. The outer function is the square root function, and that derivative is 1 over 2 times the square root of, and instead of x, the inside now is 6x minus 7 times the derivative of this inside. The derivative of the inside is just 6. And when we simplify, 6 divided by 2 is 3. So it's 3 divided by 6x minus 7. Example number 3. Let p of x equal 1 over 2x minus 1 quantity cubed. Find p prime of x. So there's a couple of ways that you could do this one. You clearly see a quotient, so you could use the quotient rule. But the top is just a constant, so normally what I would do in that case is move this term from the bottom to the top by negating the exponent. We get 2x minus 1 to the negative 3 power. Now I'm going to take the derivative. It's a power rule, so we're going to bring the negative 3 down. The inside stays the same. Lower the power by 1. Negative 3 minus 1 is negative 4 times the derivative of the inside. The derivative of the inside is 2. Negative 3 times 2 is negative 6. Return that term with the negative exponent back into the denominator. And we get 2x minus 1 quantity to the 4th power. And that's the derivative. The chain rule is one of those rules that is always in effect. You may just need to use it, and you may not. But it's always there. That's one point I wanted to make. Another point that I want to make is that all the derivatives that we've done before, the chain rule does apply to them too. We just made them so easy that the chain rule didn't change anything. So for example, suppose you have f of x is equal to x to the 6th. The derivative of this, if I sort of overdo it and use the chain rule, would be bring the 6 down, leave the inside alone, which is just x, lower the power by 1 to a 5, times the derivative of the inside. Well, the inside was just this x right here, and the derivative of x is just 1. So that's 6x to the 5th, exactly the way you expect it to be. So we were always using the chain rule, we just didn't write out the 1, and we really hardly ever do. That's another point to make. The third point is that you can chain these derivatives together. It's possible to have an outer function, and inside that is another function that itself has an outer function and an inner function. And then maybe there's 2 or 3 levels. It's like an onion. The more you peel it, the closer you get to the center. And you just keep following the chain rule. You just keep tacking on these derivatives of the inside until you get to where it would just be this simple function like 6x to the 6th is 6x to the 5th. Example number 4. Find the equation of the line tangent to p of x is equal to 9x minus 1 quantity raised to the 1/3 power at x is equal to 1. So if we're looking for a tangent line, then that tells me I need a derivative. And in order to find the equation, I know I'm going to need two parts. I'm going to need a slope, and I'm going to need the actual point that the function passes through at the target, which is x equals 1. So let's start with the function itself. P of x is equal to 9x minus 1 to the 1/3 power. To find the slope, we need the derivative. So p prime of x is equal to 1/3 times 9x minus 1. Inside stays the same. Lower the power by 1. 1/3 minus 1 is negative 2/3. Times the derivative of the inside. The derivative of the inside is 9. Let's simplify a little bit. 1/3 times 9 is 3. 9x minus 1 to the negative 2/3 power. You can write that in the bottom, or you can leave it, since we're not really interested in what the derivative is. We just need to use the derivative to find the value. So we're going to have p prime of 1, that's the target x value. And let's figure out what this x value is. It's 3 times 9 times 1 minus 1, all raised to the negative 2/3 power. That would be 3 times 8 to the negative 2/3 power. And that would be 3 divided by 4, 3/4. Because 8 to the negative 2/3 power is 1/4. So the 4 goes to the bottom, 3 stays in the top. So there's the slope. It's 3/4. To find the point, I evaluate the target number in the original function, p of 1. P of 1 would be 9 times 1 minus 1 to the 1/3 power. 9 times 1 minus 1 is 8. 8 to the 1/3 power is 2, because 1/3 is the cube root, and the cube root of 8 is 2. So this tells me that the point is 1, 2. And now to find the equation, we just use slope-intercept form. So it's y equals mx plus b. Plug in the 2, plug in the 3/4, plug in the 1, solve for b, and we get b is equal to 5/4. And so the equation is y equals 3/4 x plus 5/4. Example number 5. The gross earnings of a company T years since 2016 are given by f of t is equal to the square root of 12t squared plus 6t plus 300 millions of dollars. A, find the gross earnings for 2018. So t is a relative variable. T represents the number of years since 2016. We're looking for earnings in 2018. This is just about the earnings themselves. It's not about the rate, so we have to use the original function itself. So 2018 is t equals 2. Gross earnings means use f, so we're looking for f of 2. 12 times 2 squared plus 6 times 2 plus 300. And if you work that out in the calculator, you get 22.450, which means $22.450 million. So $22.45 million. Part B, Find the rate the gross earnings are changing in 2018. So again, 2018 is t equals 2. Rate says take a derivative. So let's find the derivative of that function first. F prime of t. And the question is, what is the outer function? Well, the outer function is the square root function. The derivative of a square root function is 1 over 2 times the square root of 12t squared plus 6t plus 300. The inside staying the same. Times the derivative of the inside. So the derivative of 12t squared plus 6t is 24t plus 6. I can simplify this by dividing the 2 into the 24t plus 6. That leaves me with 12t plus 3, all divided by the square root of 12t squared plus 6t plus 300. To find the rate that the gross earnings are changing in 2018, we evaluate the derivative at t equals 2. So this becomes 12 times 2 plus 3 over the square root of 12 times 2 squared plus 6 times 2 plus 300. And that is equal to 1.203, which we translate and interpret to be that gross earnings are, because the derivative is positive, we say that they are increasing. At the rate of $1.203 million per, and then what was the time frame for the t? It was years per year. So it's $1.203 million per year. There's another way of formulating the chain rule, and it uses the Leibniz fractional notation for derivatives. So let's suppose that you have sort of this chain of functions. You have y is a function of u, and u is a function of x. And what you'd really like to know is, how does y change with respect to the x? Sort of going over the u and skipping it. Skipping the middleman, really. Well, you can use these Leibniz fractional notations for derivatives like they were really fractions. And the way to think about it is that dy dx is equal to dy du times du dx. In some sense, you can think of it like the du's are going to cancel and leave you with dy dx. Okay, that's the way you think about it. That's not what you do, but that is what you think about. All right, so let's see an example with just straight up algebra. Example 6, let y equal u to the 7th plus 3u, and u is equal to 2x squared plus 5. Find dy dx. So I'm going to have to go through the u to get this. So dy dx is dy du. And I can do that because I have a function with y is equal to some function of u's. Times du dx. And I can do that one because I have a u function that is a function of x's. All right, so whatever variable is on top is what it's equal to, and the variable on the bottom is the independent variable for that equation. Now I just work out these different things. Dy du is the derivative of the y equals a function of u function. So that would be 7u to the 6th plus 3. That's the derivative of this function here. Times, now I need du dx. That is going to be the derivative of the second function here. And the derivative of that is 4x. And that looks great, except one slight thing. We're looking for dy dx, which indicates I need only x's in my solution, and I still have y's. But luckily, I know exactly what y is. Y is equal to 2x squared plus 5. So I'm going to substitute that value for my u. So my u right here is going to be substituted out with 2x squared plus 5. Raise that to the 6th, add 3, and then multiply by 4x. And there you go. Not much simplifying we can do. We've got a 6 power on the inside. We got a plus 3. We could do a little bit of simplifying, but not too much. So let's just leave that one there. But that's how you use this expanded chain notation. You got to make sure the functions are organized just right and that they sort of cancel numerator and denominator to get the one you're looking for. They don't technically cancel, but it looks like it, so you can use that as a mnemonic. Example number 7. A factory has modeled the total cost of manufacturing X units with the function C of X is equal to 0.5x squared plus 4x plus $1,200. Additionally, the factory produces X of T equal to T squared plus 80T units during the first T hours of a production run. Compute the rate at which the total cost is changing with respect to time 3 hours after production begins. This one is very complicated. Let's analyze. The question is asking to compute the rate, so that means derivative, at which the total cost, which is C, is changing with respect to. With respect to is key about what goes on top and what goes on bottom. So total cost goes on top because it was first, is changing with respect to time. So T goes on bottom. So this is dc dt. That is how you would interpret this piece of the question. Total cost changing with respect to time. Then 3 hours after production begins, that means T is equal to 3. So it seems easy enough until you look at the actual equations that you were given. dc dt means to take the derivative of the c function with respect to t. But there are no t's in the c function. So that can't work. So what we're going to do is we're going to use the chain rule to rewrite this as dc, and then what variable do I have with my c function? dx. And then notice I've got this x function that's a function of t. And that becomes dx dt. And sure enough, if you think about it, the dx's would cancel, leaving you with dc over dt. So we don't do that, but we use these derivatives to help us compute the result. So let's do that. So what is dc dx? That's the derivative of the c function. So 1/2 x squared, if you bring the 2 down, 2 times 1/2 is just 1. So this actually is just x. It's x to the first, or 1x to the first. We just write x. Plus 4. The derivative of 1200 goes to 0. Times dx dt. That's the derivative of the x function with respect to t. So this is going to be 2t plus 80. That is the derivative, except that we want it in terms of t. We still have an x. Got to get rid of that x. So I'm going to rewrite this as what was x equal to in terms of t? That was t squared plus 80t. And then plus the 4, everything else is the same. Now I have my derivative in terms of t, and now I can evaluate where t is equal to 3. So let me show you a little piece of notation here. dc dt, you use a big vertical bar to the right side, and a subscript of t equals 3 indicates that you want to take the function on the left, dc dt, and evaluate it at t is equal to 3. It's like f of something, but since you don't have an of with a dc dt, you have to use this. So we're going to plug in the 3. 3 squared plus 80 times 3 plus 4. 2 times 3 plus 80. Work all that out. The answer is 21,758. Now we need the units. Okay, so the cost, let's look at our derivative. So it's cost per time. So it's going to be dollars per hour. You go back and you look and see what unit C was in. It was in straight dollars, not thousands or millions or anything like that. It was just straight dollars. And T was measured in time. Now, notice what was sort of skipped over here. The X. The X was the middle guy. And the middle guy didn't even get any consideration here at the end. The middle guy was in units, factory units like widgets or skateboards or whatever. That's out. Didn't even bother with it. So it's now $21,758 per hour. All right. Thanks for watching. Be sure to like and subscribe.